A novel framework for robust tracking control of nonlinear dynamic systems is presented, aiming to achieve optimal performance in the presence of disturbances and modeling uncertainties. The proposed method utilizes a robust linear quadratic tracking (LQT) controller design based on a Youla-type filter (Q). This filter enables the incorporation of an additional gain factor, which balances LQT performance and robustness with respect to disturbances and uncertainties. The gain factor is optimized using a data-driven extremum seeking approach, a model-free optimization method that minimizes the tracking cost. This optimization approach eliminates the need for explicit system modeling, allowing for effective handling of complex nonlinear dynamics and uncertainties. The effectiveness of the proposed framework is validated through simulation on a Furuta inverted pendulum, a highly nonlinear and unstable system. Results demonstrate significant transient tracking performance improvement compared to standard LQT and H1 controllers. The optimal gain factor is shown to be dependent on the nonlinear dynamics, reference trajectories, and disturbances, highlighting the importance of adaptability in robust tracking control. The proposed framework offers a robust and adaptive solution for tracking control of nonlinear dynamic systems, with potential applications in various fields, including robotics, aerospace, and process control. By leveraging the strengths of LQT and ES, this approach provides a promising direction for addressing the challenges of robust tracking control in the presence of uncertainties and disturbances. Nonlinear systems with disturbances and modeling uncertainties are addressed through a robust linear quadratic tracking controller design. The system, comprising a nonlinear plant with a linearized form, incorporates an observer and a filter Q to enhance robustness against disturbances. The control objective is to minimize a finite-time quadratic cost function, ensuring the output tracks a desired reference trajectory. The proposed approach involves a two-step design process. First, a robust LQT controller is designed based on the Youla-type filter Q. Then, an extra gain factor is introduced to the filter and tuned using data-driven optimization algorithms, such as extremum seeking. The controller structure consists of a nominal control UL, an observer, and the filter Q. The nominal control UL stabilizes the system without considering disturbances, while the filter Q produces an additional control input UF to enhance robustness. The filter Q is obtained using standard H1 techniques for the augmented system with state x, e, where e equals x represents the estimation error. The paper highlights the importance of balancing robustness with respect to disturbances and LQ optimal tracking control. An optimal control input is necessary to minimize the quadratic cost function, which is achieved through the proposed two-step approach. The use of data-driven optimization algorithms in the second step enables adaptive tuning of the gain factor, making the controller more effective in real-world applications where disturbances and uncertainties are inevitable. The design of a robust linear quadratic tracking (LQT) controller with a parameterized filter tilde Q is presented. For linear time invariant (LTI) systems, the optimal control input is derived using the Hamilton-Jacobi-Bellman equation, involving the solution of a differential Riccati equation to obtain the control gain F in practice. A simplified algebraic Riccati equation can be used to obtain a time-invariant stabilizing control gain. To enhance robustness, an extra gain factor 2R is introduced to the filter tilde Q, resulting in a new filter tilde Q, allowing for a balance between LQT and robustness. The tracking performance index J, U, is now a function of the gain factor, and the goal is to find an optimal parameter to minimize this cost function. A theorem is presented, stating that if the origin is an equilibrium point for the nonlinear system and the system is locally asymptotically stable, then the closed-loop system is also locally asymptotically stable for any greater than 0, ensuring stability in the presence of disturbances and linearization errors. To solve the optimization problem for nonlinear systems, an extremum seeking algorithm is proposed. This data-driven approach does not require knowledge of the system model and can be applied online to adjust the control parameters based on real-time data. The ES algorithm iteratively updates the parameter to minimize the cost function J and ensure optimal tracking performance. Overall, the design of a robust LQT controller with a parameterized filter tilde Q is outlined, which can be optimized using an ES algorithm for nonlinear systems, offering a balance between tracking capability and robustness against disturbances and linearization errors. Designing a robust optimal tracking control scheme for nonlinear systems requires careful consideration of transient behavior in the closed-loop system. To address this, a linearized model of the nonlinear system around the origin is first introduced, followed by the design of a linear quadratic tracking (LQT) controller with a parameterized tilde q. Notably, the choice of this parameter does not impact local stability properties but significantly affects performance, particularly in transient phases. To optimize performance, a data-driven extremum seeking S algorithm is employed to tune the parameter for a given disturbance. This algorithm iteratively updates the parameter to minimize a cost function, defined as J, which is a function of the system's transient behavior. The proposed robust optimal tracking control scheme involves a three-step design procedure: obtaining the linearized model, designing the LQT controller, and tuning the parameter via the ES algorithm. It is crucial to account for unmodeled uncertainties and deterministic noises in the linearized model, as these can substantially impact system performance. Assuming a unique optimal parameter exists for a given disturbance, the S algorithm converges to this optimal value. Figure 5 summarizes the ES tuning scheme, where the parameter is iteratively updated to minimize the cost function J. The primary focus of this work is to ensure optimal transient behavior in the closed-loop system, and the proposed method provides a robust and efficient means of achieving this goal. This section of the research paper applies the proposed robust tracking control algorithm to a Furuta inverted pendulum system. The pendulum system is modeled using nonlinear equations of motion, which are then linearized around the equilibrium point. A linear quadratic tracking (LQT) controller is designed based on the linearization model, with closed-loop poles and observer gain L chosen to achieve stability. A filter tilde Q is also designed to satisfy the H1 performance criterion, with a performance bound of 0.21. Simulation results for the Furuta pendulum system under different disturbance signals and reference signals are presented. Two types of disturbances are considered: a square wave with an amplitude of 2 and a frequency of 0.5 Hz, denoted as W1, and a vanishing signal W2, T, equals 5e0.1 T. Two reference signals are also considered. Case A tracks a square wave with an amplitude of 20 degrees and a frequency of 0.05 Hz, while Case B tracks a sinusoidal signal R equals pi, 3 sin, pi t. The quadratic cost function J, theta, in equation 15, is used with t equals 20s, and the parameters A, h, and epsilon in the ES algorithm are set to A equals 0.8, h equals 0.1, and epsilon equals 0.015. The step size delta in the ES algorithm depends on the specific disturbance signal and reference signal. The optimal theta tuned via S is denoted as theta. Table 2 summarizes the theta values in which minimum costs are reached for case A and case B in the presence of W1 and W2. Figures 6 and 7 show that S minimizes the cost function, 15, with convergence to the parameter theta that produces a minimum for case A and case B in the presence of W1, respectively. It can be seen that the controller with theta improves the tracking performance significantly compared to the initial guess theta, 0, equals 1. This research paper presents a novel tracking control scheme for a class of nonlinear systems, which are subject to disturbances. The proposed method utilizes a robust controller with a Youla-type filter Q and the data-driven extremum seeking S technique. An innovative feature of this approach is the introduction of a gain factor, lambda, to the filter Q, providing an additional degree of freedom that can be optimized for tracking performance. The simulation results demonstrate that the proposed tracking controller, when combined with a tuned lambda via ES, can achieve optimal tracking performance for nonlinear systems in the presence of disturbances. A review of relevant literature on control theory is also provided, including robust and optimal control, H2 and H1 control problems, and extremum seeking control for discrete time systems. The proposed approach is compared to other methods such as LQT and H1 performance, showing superior transient behavior in the presence of deterministic uncertainties and linearization errors. The paper concludes by highlighting the effectiveness of the proposed S algorithm in dealing with disturbances and linearization errors, and suggests potential future work in the field of control theory. The research contributes to the advancement of control schemes for nonlinear systems, providing a new paradigm for robust, high-performance, and fault-tolerant control. This innovative method offers a promising solution for addressing the challenges posed by disturbances and linearization errors in complex systems, paving the way for further exploration and development in the field of control theory.